Good afternoon. So I report about operation amplifiers characteristic. So module 6.4 operation amplifiers characteristic. So we have supply voltage. Two types of supply are used for operation amplifiers, the dual and single supply. Many operation amplifiers, especially older types, use a dual supply. Cross parentheses positive Vs and negative Vs cross parentheses often in the 12 to 18 range. This allows a zero difference between the input terminals to produce a zero voltage output and an output signal to swing both positive and negative with respect to ground. So mo ni siya dapit aning dual supply. So mo na siya both positive and negative with respect to ground. Single voltage supplies have grown in popularity with the increase in portable battery operated and or automotive devices where dual supply using multiple batteries are more expensive to implement. A zero difference between the input terminals on these devices will produce an output at half supply, allowing an output signal to swing between supply and ground. So, supply voltage meaning the root mean square value of electrical potential between two conductors. High voltage bus means the electrical circuit including the coupling system for charging the wrist that operates on high voltage. So the second is frequency response. An important characteristic of any amplifier is its frequency response. In the ideal amplifier, its frequency response should be infinite. It will amplify any and all frequency equally. In practical amplifiers, this is difficult, impossible to achieve, and not always desirable, but operation amplifiers have extremely wide and easily variable bandwidths. So kani nga picture mo ni siya depende sa frequency amplifiers kay nasa below. So mo ni siya naka decrease sa open loop gain. So frequency response of the operation amplifiers in open loop configuration, the gain of the operation amplifiers is not constant and varies with the frequency, and the product of gain and frequency remains constant till the unity gain frequency for the operation amplifiers, which is known as the gain bandwidth product of the operation amplifiers. Figure 6.41 Typical operation amplifiers frequency response. Open loop voltage gain. Figure 6.41 shows the frequency response of a typical operation amplifiers LMC 660, which confirms that the open loop gain with no feedback at very low frequency is hugged. When open loop gain is quoted, it refers to the maximum AC gain at very low frequency. It can be seen from Figure 6.41 that the LMC 660, for example, has an open loop gain voltage about 126 dB, a voltage gain of nearly 2 million, but at frequency above few Hz or high frequency gain begins to fall rapidly. 20 40 dB decayed until 1.4 mHz high frequency, the gain has reduced to 0 dB, a voltage gain of X1. So open loop voltage gain, usually called AVOL or AVOL, sometimes simply AV for most VFB operation amplifiers, is quite high. Common values are 100,000 to 100,000 million and 10 or 100 times these figures for high precision parts. So, natay video para mas kuan siya ang open loop voltage.
In this video, we look at the effect of a non-infinite open loop gain on the inverting amplifier. In other words, we're going to be looking at the inverting amplifier configuration, only now, instead of having A naught be infinite, it's going to be some number less than infinity. Probably still large, but less than infinity. The operational amplifier is a difference amplifier that multiplies the difference between Vp and Vn, or the output V out is equal to A naught times V sub P minus V sub N. Again, in the ideal amplifier configuration, or the ideal amplifier model, we say that A naught is infinite and the difference between the two is virtually zero. And so we have this indeterminate form, infinity times zero, but we calculated the gain using these ideal op-amp approximations. We found the gain to be negative R2 over R1. But in this video, we're going to look at the effect of a finite A0. In other words, V out will in fact equal this A naught times Vp minus V sub n, but V sub p is grounded, so V naught is going to equal A naught times 0 minus V sub n, so we'll just have a minus V sub n. That's an n term there. Or we can then solve for V sub n. The voltage at the inverting terminal, V sub n, is equal to V out over negative A naught. So we now have, using this expression here, we've calculated an expression for V sub n. You'll notice because A naught is not infinite, the voltage here is not exactly the same as the voltage at the non-inverting terminal. In other words, that ideal op-amp approximation that we've been using, that says that the virtual short approximation that comes from in the ideal op-amp model is a result of having an infinite gain. So now that we've reduced that gain from infinite to some finite number, the voltage across here is not going to be zero. And in fact, we've calculated an expression for the voltage there to be negative V naught over A naught. Now with that, let's go ahead and come up with an expression for V out. And to do that, we're going to start at this expression right here, or the voltage at this node, which we have in terms of V naught. And then we can determine V out by adding to this term, or subtracting from this term, the voltage drop across R2. But to do that, we need to know what the current here is. And because the current here is the same as the current there, we need to determine what I1 is. Again, because the current going in here is zero, we're not relaxing that ideal op-amp approximation. We're still saying the current going into the amplifier is zero. So the current I1 will be the current coming up here through I2. It's easier to do it than to say it. Let's just go ahead and do this. So I1 will equal the voltage drop across R1 divided by R1. Well, the voltage drop across R1 is going to be V in minus the voltage here, which is minus V out over A naught, divided by R1. So now, as I was saying, we can say then that V out is equal to this voltage right there, negative V out over A naught. And then because we're going in the direction of current flow, we'll be seeing a voltage drop from here to there. So it'll be minus I1 times R2. Now let's go ahead and substitute in the expression for I1. We have then V naught is equal to negative V naught over A naught minus, now I2, or I1 rather, is this expression right there. So minus R2 times I1, the R2 times I1, which is Vn minus a minus is a plus V naught over A naught divided by R1. And this isn't an R1, this is an R2. R2. So let's just make sure we did this right. We've got then this negative V naught over A naught minus R2 times I1, but I1 is Vn minus a minus is a plus, so Vn minus V naught over A naught, all divided by R1. Now we can combine like terms.
So large signal voltage gain. The large signal voltage gain is usually quoted in preference to the open loop voltage gain. This is the open loop voltage gain measured at DC with the amplifier producing a large, just less than maximum voltage output, usually quoted in #MV figures. For large signal voltage gain can cover a wide range for given operation amplifiers depending on design variant and factors such as minimum or maximum operating temperature. So the large signal voltage gain is usually quoted in preference to the open loop voltage gain. This is the open loop voltage gain measured at DC. So sakop nagyapon ni siya sa open loop voltage gain. So very same as po ni siya with the amplifier producing a large, just less than maximum voltage output, usually quoted in VMV. The gain that produces a peak-to-peak signal output equal to the difference between the positive and negative supply voltage measured in dB. Closed-loop voltage gain. In practice, the Hog gain of an operation amplifiers is greatly reduced by applying an appropriate amount of negative feedback. In this way, an impressively level response can be achieved, extending from DC (0 frequency high to any frequency up to about 1 M frequency high or more, as well as the added benefits of reduced noise and distortion. The blue dotted line shows the response of the operation amplifiers with negative feedback. The gain has been reduced to 20 dB. A closed-loop voltage gain (ACL) of X10, which has produced a flat response from 0 frequency high to about 140 K frequency high. Closed-loop gain is the gain of the amplifier with feedback loop close as opposite. So opposite na siya gyapon sa open loop gain, which is the gain with the feedback loop. Open closed loop gain has two forms: signal gain and noise gain. Gain bandwidth product. As the closed-loop gain and the small signal bandwidth of an operation amplifier are closely related, the parameter gain bandwidth product is often used to better describe the possible combination of gain and bandwidth. The graph of the open lobe frequency response in figure 6.41 therefore plots all those points where voltage gain x bandwidth equals 1.4 million frequency high. For example, 140 key frequency high bandwidth multiplied by voltage gain of 10 also gives a gain bandwidth product of. So mao ni siya formula sa ubos kaning 10x 140 key frequency high, so equals to 1.4 million frequency high. So mao ni siya ang solution sa below. So note the bandwidth indicated by the gain bandwidth product applies to small signal, but when large AC signal are involved, especially signal with fast rising and falling edges, the bandwidth may be further reduced by the slow rate, then the power bandwidth becomes more relevant. So natay additional video para mas makaibaw ta kung unsa jud siya gain bandwidth product.
In this video, we will see what the gain bandwidth product, one of the figures of merit of an amplifier, is. We'll analyze the frequency response of an op-amp and explore its speed limitations. So far we have not considered frequency as a factor in any of our analysis. That is, we've considered the gain of the op-amp to be constant for any value of signal frequency. In reality, due to the internal capacitances of the op-amp, the value of gain degrades for higher values of frequency. Typically, as shown, the gain of an op-amp remains constant up to a certain value of frequency. We call this value the cutoff or corner frequency of the op-amp. The range of frequencies for which the gain of an op-amp remains constant is referred to as the bandwidth of the op-amp. After the cutoff frequency, on a log scale graph, the gain reduces at a rate of 20 decibels per decade. For simplicity, we can model the internal circuitry of an op-amp as a single pole system. If the pole is at omega naught, the transfer function becomes A naught, upon 1 plus S by omega naught. Hence, at frequencies well below omega naught, the gain of the op-amp is A naught. Note that the corner frequency for a first-order system is given by the value of its pole. The gain decreases as the frequency crosses omega naught and eventually falls to unity at the frequency, say omega u. This frequency is called the unity gain bandwidth of the op-amp and has a value of A naught, into omega naught. That is, the unity gain bandwidth is the DC gain multiplied by the cutoff frequency. Hence, it is also known as the gain bandwidth product. The unity gain bandwidth is typically considered as a figure of merit for an amplifier. Till now we have been analyzing an open-loop op-amp. Now, using our newly developed model, let's analyze an op-amp in a closed loop. Consider a non-inverting amplifier. If we consider the gain to be finite, the gain is given by A upon 1 plus, or 1 upon R1 plus R2, into A. We replace A by the single pole model mentioned before. Substituting A naught, upon 1 plus S by omega naught in place of A, we get the following expression. Multiplying the numerator and denominator by 1 plus S by omega naught, and rearranging a bit, we get. This is a first-order system with the pole at omega naught, into 1 plus or 1 upon R1 plus R2, into A naught. The DC gain is now A naught, upon 1 plus or 1 upon R1 plus R2, into A naught. Hence, the closed-loop gain is significantly smaller than the open-loop gain, while the closed-loop pole is much larger than the open-loop pole. Hence, we have a trade-off between gain and bandwidth. If we wish to increase one, we must reduce the other. Let's try to find the unity gain bandwidth of this circuit. We already found out that the unity gain bandwidth is given by the product of the DC gain and cutoff frequency. Multiplying these two, we get omega u as A naught into omega naught. This is exactly the same as before. Hence, placing the op-amp in negative feedback does not seem to affect the unity gain bandwidth. In the figure shown, the yellow curve represents the op-amp in open loop and the red curve represents the op-amp in closed loop. In other words, the gain bandwidth product of an op-amp is the same, irrespective of whether it is an open loop or closed loop. That's all for the frequency response and gain bandwidth product of an op-amp. If you have any questions, please ask in the comments section below. Don't forget to like, share and subscribe.
Maximum differential input. This is the maximum voltage that can be applied between the two inputs of some devices. This can be equal to the supply voltage, but on others it can be considerably less. So maximum differential input, these operation amplifiers will generally have internal back-to-back diodes across the inputs. This will not always show up in the simplified schematics of the amplifiers. It will show up, however, as a differential input voltage specification of plus and minus 700 and voltage maximum. Input resistance. This is the resistance looking into the input terminals with the amplifier operating without feedback. Open loop typical resistance for bipolar devices are in the range of 1M uppercase to 10N uppercase for FET or FET, and CMOS types or CMOS resistance are much higher and range up to 101 to uppercase or more. So the input resistance of the ideal operation amplifiers is infinite. However, the input resistance to a circuit composed of an ideal operation amplifiers connected to external components is not infinite. So here's a video of input resistance.
Let's take a look now at the input resistance of two of our common operational amplifier configurations, the non-inverting and the inverting. You'll recall from our discussion of just the generic amplifiers that in general we have a source with a source resistor that we want to amplify, and that then is connected to the input resistance and to the output. If this is Vin, the output is some scaled AV0 times Vin. So between the source resistance of the source and the input resistance of the amplifier, we've got a voltage divider. And in order to make it so that this voltage here is a significant portion of this, we want the input resistance here to be significantly larger than the source resistance. In fact, ideally, this input resistance would be infinite. So what we want to look at is, what are the input resistances that these sources see in both the non-inverting and the inverting configuration? Well, our input is just equal to the input voltage divided by the input current. Now, in this case, V2 is our input source, our signal, and we haven't shown a resistance, but there could very well be, and in all likelihood there is a source resistance associated with it. But because the current, or because this terminal is source is connected directly to the non-inverting terminal that has, in the ideal case, an infinite input resistance, the current going in, IN, is going to equal 0. So for the non-inverting configuration, we have Rn is equal to Vn, which is just V2 divided by In, which is 0. So the input resistance for the non-inverting amplifier is infinite. And when it comes to this type of a voltage division, the voltage across the input resistance will be equal to the signal voltage because there's no current flowing between them. Now, let's determine the input resistance for the inverting amplifier. We're going to see that it's not nearly as satisfying as this infinite resistance on the non-inverting. Once again, we have the voltage Vin, which in this case is V1, and we have a current flowing from the source into the amplifier, calling that In. But because this doesn't go directly and solely into the inverting terminal, because there's this path, In is not 0. Rather, In is equal to Vin, or V1, if you will, divided by R1. So, Rin is equal to the input voltage, which is V1, divided by In. Well, this then is equal to V1 divided by In, which is V1 divided by R1. Well, dividing by a fraction, you invert and multiply, the V1s cancel, and we see that the input resistance is simply R1, whatever the value of that resistor is there. Well, what's the problem with that? In order to make the input resistance to the inverting amplifier large, where the input resistance is just R1, we'd have to make R1 large. If we wanted it, say, to be on the order of a megaohm, we'd have to make R1 be 1 megaohm. Well, that in and of itself isn't a problem. Where does the problem come from? Well, the problem comes from that the gain, the closed-loop gain of this amplifier, is equal to a negative R2 over R1 times V1. So if we want to get any gain at all out of this thing, R2 has got to be bigger than R1. Well, if R1 is 1 megaohm and we want a gain of 5, R2 is going to have to be 5 megaohms. Well, that represents a couple of problems. First of all, it's tough to get highly precise, big resistances. But the other problem is that when we start having resistors around here on the order of megaohms, the current flowing through here is so small. After all, that's what we were trying to get it to be. We wanted that current to be small, so we made these resistances large. The problem is, as we have said before, the current going into the terminals of the op-amp is really small, but it's not 0. In fact, the currents coming into the op-amp might be on the order of a few tenths of a microamp. Now, if these are megaohm resistances, this current here is also going to be on the order of microamps or tenths of microamps. And all of a sudden, the current here is no longer significantly larger than the current here, so that we can just ignore this. Let's state it the other way. No longer is this current here going into the inverting terminal of the amplifier, no longer is it so much smaller than the other ones around it, the other currents around it, that we can just neglect it. So at some point, these resistances cause such small currents that this current and this current are going to be on the same order, and we can no longer ignore that current. One of the inherent weaknesses of the inverting amplifier as it's drawn here is that it has a relatively small input resistance. There are some tricks that you can do, we'll talk about them in class, but there's tricks that you can do to increase the effective input resistance seen by the source.
So, input offset current. The currents flowing into the two inputs should ideally both be 0, but for practical operation amplifiers, although the input currents are still extremely small, they do exist and may also be different. Unequal currents cause different voltages at the inputs, and when this small difference in a voltage is amplified, it causes the output to be other than 0. To overcome this effect, an input offset voltage can be applied between the inputs to correct the output voltage to 0. Typical values for bipolar operation amplifiers would be plus minus 1 M voltage ranging up to 15 M voltage for FET types. The input offset current IOS is the difference between 1B and 1B positive, or IOS equals 1B positive and negative 1B. Note also that IOS is only meaningful where the two individual bias currents are fundamentally reasonably will match. To begin with, this is true for most voltage feedback or VFB operation amplifiers. So, not a video about input offset current.
In this video, we'll look at what input offset voltages are. Input offset voltages are one of the most common imperfections present in practical op-amps. If we take an open-loop op-amp and ground both the input terminals, ideally we should get 0 voltage at the output. However, in real op-amps, despite having 0 differential input, we still get some finite output. This output is due to the offset voltages present at the input of the op-amp. To understand why we get this offset voltage, we need to take a look at the internal structure of the op-amp. The first stage of an op-amp consists of a differential amplifier. Differential amplifiers ideally need to be symmetric. However, during fabrication and packaging, several mismatches occur. Hence, even if we apply the same input to both the terminals, that is 0 differential input, the bipolar transistors sensing the two inputs may display slightly different base emitter voltages, what we call biasing voltages. The same effect occurs for MOSFETs. Thus, the op-amp sees a differential input and amplifies this, to give us some offset output. We can cancel the effect of the input offset voltage by applying a differential input of the same value in the opposite polarity. Thus, the input offset voltage VOS is defined as the differential input voltage we are required to apply, so that we get 0 voltage level at the output. We model the input offset voltage by a voltage source of value VOS, applied to any one terminal of the op-amp. As input offsets are arbitrary, we cannot determine their polarity beforehand. Hence, we can model the offset voltage at any terminal. Offset voltages can range from 1 mV for low precision op-amps and can go as low to a few microvolts for high precision op-amps. Why are DC offset voltages important? Let's take the example of the non-inverting amplifier. In the presence of op-amp offsets, the non-inverting amplifier now sees an input of Vin plus VOS. Hence, the output becomes 1 plus or 2 by R1, into Vin plus VOS. This means that the op-amp not only amplifies the input, but also the offset voltage, leading to severe inaccuracies. Suppose the value of Vin is 1 mV and the value of the input offset voltage is 0.1 mV. If the gain of the circuit is 10, then the Vin will be amplified to 10 mV and VOS will be amplified to 1 mV. As we do not know the exact polarity of VOS, we tend to write the output as 10, plus or minus 1. That is, the output can be 9 mV or 11 mV. Input offset voltages affect inverting amplifiers in a similar manner. As the gain of the op-amp increases, so does the offset voltage at the output, which leads to higher inaccuracies. This is especially a problem in circuits dealing with low voltage applications. It is also a problem for data converter circuits, which require a high amount of precision. So, we need to find a way to eliminate this offset voltage. The first thing we can do is use a high precision op-amp. However, this can increase the cost of the circuit. The second thing we can do is use DC offset nulling circuits. If you look at the IC741 pin diagram, you can notice two pins labeled as offset null. We can nullify the effect of the input offset voltage by applying a potentiometer between these terminals and adjusting its value till we get zero output. That's all for this video. If you have any doubts, feel free to ask in the comments section below. Don't forget to like, share and subscribe.
So temperature coefficients, both the input offset current and input offset voltage are affected by changes in temperature and tend to drift higher as temperature increases. The temperature coefficient of input offset current measured in NA or PA degrees Celsius, while the temperature coefficient of input offset voltage is usually measured in micro degrees Celsius. So temperature coefficient seems to have no effect on the input impedance of the operation amplifier circuit. Temperature has no effect on the needed power to disturb the operation circuit. Power in dBm needed to disturb the operation amplifiers varies linearly with temperature. The immunity model including temperature effects gives good result. Figure 6.4 and 2 output compensation. Slew rate. The slew rate of an operation amplifiers describe how fast the output voltage can change in response to an immediate change in voltage at the input. The higher the value in microsecond of slew rate, the faster the output can change and the more easily it can reproduce high frequency signal. So slew rate is defined as the maximum rate of change of an operation amplifier's output voltage and is given in units of volts per microsecond. Slew rate is measured by applying a large signal step such as 1 volt to the input of the operation amplifier and measuring the rate of change from 10% to 90% of the output signal amplitude. The slew rate also affects sine wave and audio signals as well as square waves. The rate of change of voltages in a sine wave is continually varying. It is changing at its fastest rate as the signal voltage crosses zero and the rate of change falls momentarily to zero. No change at both the positive and negative peaks of the wave. If the slew rate of the amplifier cannot keep up with the fastest rate of change of the signal, some distortion will be produced. So, natay video about slew rate.
In this video, we'll understand what slew rate is and what its implications on operational amplifiers are. Consider an op-amp configured in a voltage follower configuration. Suppose we give a pulse input which varies from 0 to 5 volts to this circuit. As the output follows the input, we expect the output to become a pulse instantly as well. However, in reality, the output does not change from 0 to 5 volts instantaneously. Similarly, the output does not fall from 5 volts to 0 at the negative edge instantaneously. This phenomenon is called slewing. The maximum rate at which the output of the op-amp can change is called the slew rate. The unit for slew rate is volts per seconds. However, we usually measure slew rate in terms of volts per microseconds for convenience. As we want the output to change instantaneously, we want the slew rate to be as high as possible, ideally infinity. Slewing happens due to the internal compensation capacitor of the op-amp. The capacitor takes some time to charge and discharge, which leads to a delay in the output. Let C be the value of the internal compensation capacitance. Then, the charging current IC through the capacitor is given by C into dVc by dt, where Vc is the voltage across the capacitor. Rearranging, we get dVc by dt is equal to IC by C. dVc by dt is the rate of change of voltage across the capacitor. Hence, the slew rate is given by IC by C. That is the charging or discharging current upon the value of the compensation capacitance. Usually, we consider the value of positive and negative slew rates as the same. Let's see the effect of slew rate on a pulse signal. Suppose we have a pulse of duration 10 microseconds and amplitude 5 volts. Suppose the slew rate of the op-amp is 1 volt per microsecond. Then the output will be a ramp. As the slew rate is 1 volt per microsecond, it will take 5 microseconds to reach 5 volts. After that, the output will stay constant at 5 volts, until the negative edge of the input. After this, the voltage will fall at a rate of 1 volt per microsecond. Hence, it will take 5 microseconds to become 0 again. Now consider a case, in which the slew rate is 0.5 volts per microsecond. In this case, the output will take 10 microseconds to reach 5 volts. Hence, the output will just touch 5 volt and again fall down to 0. Suppose the slew rate reduces further to 0.3 volts per microsecond. In this case, at the end of 10 microseconds, the output will have only reached a value of 3 volts. Hence, the voltage never reaches 5 volts. At the negative edge, it starts reducing from 3 volts back to 0 volts. Now consider the case of a sinusoidal signal as an input to the voltage follower. Suppose the maximum amplitude of the signal is Vmax. Then the equation of the signal can be written as Vmax sine omega t. Differentiating this with respect to time will give us the rate of change of voltage. dV by dt is equal to Vmax omega, cosine of omega t. The maximum value of this is Vmax into omega. Hence, we require an op-amp whose slew rate is greater than or equal to this value. Omega can also be written as 2 pi f. Hence minimum slew rate is equal to 2 pi into f into Vmax. Alternatively, the maximum value of frequency we can give as input to this circuit without distortions is slew rate upon 2 pi into Vmax. If we violate the slew rate condition, we will get an oscillating ramp output instead of a sinusoidal output. For example, if we have a sinusoidal output with 10 volts amplitude and a frequency of 20 kHz, then the minimum slew rate required will be 2 pi into 20,000 into 10, which comes out to 1.257 into 10 to the power 6 volts per second. That is 1.257 volts per microseconds. If the slew rate of the op-amp is greater than this value, the output will follow the input perfectly. That's all for this video. If you have any doubts, feel free to ask in the comments section below. Don't forget to like, share and subscribe.
So these are the formula of slew rate. So V and microseconds cross parentheses equals 2 PF V P key. So where F the highest signal frequency hertz and V peak key equals the maximum peak voltage of the signal. For example, if an operation amplifier is to amplify a signal with a peak amplitude of 6 volts, at a frequency of 40 kHz, an operation amplifier with a slow rate of at least 2p times 40 exp 3 times 6 equals 1.4 volts microseconds would be required. So therefore, to be sure of amplifying large amplitude signals that are most likely to produce large and fast rates of voltage change, an operation amplifier needs to have a sufficiently high value of slow rate to cope with the greatest possible rate of voltage change. If the largest possible voltage swing and the highest frequency of the signal are known, the minimum required slow rate for the operation amplifier can be calculated using this formula. Power bandwidth. Once the slow rate calculated as above for the large signal becomes equal or greater than the amplifier's slow rate, slow rate limiting starts to occur, causing reduced gain and distortion of the signal. The highest frequency that can be used to amplify a full amplitude signal before slow rate limiting is the highest frequency limit of the power bandwidth. So diba katong naa sa formula sa slow rate, so mo to siya nakakuan sa nakapan sa large signal equal or greater. So dito siya mag-base sa gi-discuss sa ato, mo ni siya gi-recap sa power bandwidth. So ang power bandwidth is the highest frequency man. So ang slow rate kay mo ni siya maka-reduce sa maka-gain siya sa signal. So these are the example of power bandwidth. For example, in an operation amplifier operating from a plus-minus 15 volts supply, the power bandwidth would be specified as the frequency range in which a plus-minus 10 volts swing can be measured at the output with total harmonic distortion of less than 5%. The power bandwidth is usually less than the small signal bandwidth indicated by the graph of the closed loop gain. And in many cases, the major factor in specifying the amplifier bandwidth. So, kani siya kay naka-indicate gyapon ni siya sa graph closed loop gain. So, mo ni siya usually nga makaless sa small signal kani nga power bandwidth.